compare notes with him, but I just tried to second guess what he might have talked about and tried to make it a little bit different. There's bound to be overlaps, since it's a similar. Okay. Now I know this is a scientifically literate crowd, but maybe not a completely geochemically literate crowd here. And I've given on this talks on this topic at this sort of geochemistry level, and the first two times I've given on this topic were to geochemists. That was fine. And the last time was to a broader range of people, about half biologists, a few geologists, some physicists, and chemists. And I was told that half the audience didn't know what the hell I was talking about. So I'm going to I tried to fix that this time. Anyway, as David was saying, I'm now at the Department of Natural Sciences downtown faculty. This research that I'm going to talk about, and the topic I'm going to talk about, I started in on while I was at the Lunar and Planetary Institute, and I need to give some credit to some other people that are that I've worked with over the years. Alan Treeman and Walter Kiefer, who are still at the institute, as well as some very, very hardworking student assistants that helped out with acquiring data. Okay, now what I want to do, I'm going to get specific and then get general, and then get specific and then get general again. I want to talk about, because the title of the talk is about experiments. So I'm going to describe some geochemical experiments where we take what we think is the composition of a Martian lava that's a direct melt from the mantle of Mars, and do some things to it, subject it to Martian upper mantle. And then I want to discuss implications for these results, and as well as results of other experiments for the state of the Martian mantle. And then I want to go through some of the data set. That's how I'm getting specific for Martian meteorites. That's how we know what the Martian rocks are actually made out of, and pertaining to the results. And then get general again, look at the pros and cons of other. If there's time, I'll discuss some future. Okay, so all of this is really, our starting point here is for the Martian meteorites, the so-called SNCs, which for the longest time stand for meteorites are named by their type locality, and then they tend to be grouped into meteorites that are similar to each other. And this whole group of rocks dating back into the late 60s was noted they were really different from other meteorites, not the least of which is they didn't look like they came from an asteroid, and they were fairly young. In other words, not dating all the way back to the earliest portion of the earliest history of the solar system. The young, some of them are a billion or so years old, some of them tens of millions. But in any case, it's hard to explain why this would be in terms of something coming from an asteroid. And growing evidence, basically throughout the 1980s, led to the general and widespread conclusion, well-accepted conclusion, that the rocks were indeed pieces of Mars that had been launched off of Mars by a large impact and made their way to the Earth. So there's been over 35. I've kind of lost count. That number may have gone up in the last few months. I don't know. And most of these are what we call mafic igneous rocks. Of course, an igneous rock is a rock that is a melt that solidifies from a melt, whether it's from a lava flow or some intrusive rock or some sort of thing like that. And mafic just stands for the fact that it's high in magnesium and iron, indicating that it's probably a melt of a planetary mantle. Now there's several categories. Again, these were called the SNCs for Shergotite, Knocklite, Shawsignite, and I'm going to focus on the Shergotites tonight. The Shergotites are broadly basaltic, and that means that a direct mantle melts. I'll come back to that in a second. There are the others, the Knocklites, which are basically, these are all related. They're all some sort of melt that came probably originally from the mantle of Mars and got in place somehow, and in some cases evolved. So the noclides, we have certain minerals called clinopyroxenes, which would crystallize out of a melt, and that's what those are made of. Gaussianites are olivine. And then there's another one that doesn't really quite. There's a couple others that don't fit into these categories. But in any case, we're going to concentrate on the shergottites and a subset of the shergottites called the olivine ferric shergottite. Now, the evidence for their Martian origin, not only their young ages compared to other meteorites, but of course we've got data from spacecraft landers. The first of which were the Viking landers, which sampled the Martian atmosphere. And we found, at least in some of these, isotopic tracers, geochemical tracers that really pinpoint their origin as Mars. That the atmosphere of Mars has some very, very singular, unusual features to it, and left its signature. Okay, here's the first meteorite, and there's a couple of others that we'll talk about. This little tiny guy is Yamato 980-459. That's a very, very warm and fuzzy name, isn't it? It's named after the Yamato Mountains. Most meteorites, a large number of meteorites these days, are found in the Antarctic because that's a good place to collect meteorites. They fall on the ice cap, and they make their way along the glacier, and as the glacier evaporates away, it leaves behind meteorites, and there's nothing else around, no other rocks source around, and so people go around with helicopters and snowmobiles and find accumulations of rocks. So this is at the Yamato Mountains and was obtained by a Japanese expedition. Now this thing is a very, very unusual rock. And it's unusual in that it appears as though not much happened to it since it came out of the it formed as a melt inside of the Martian mantle and erupted to the surface, and that's unusual in itself. But that's very good for us because we think we're looking at something that is telling us that this is really a pristine, what we call primitive composition that we can relate directly to the composition of the mantle, and that's going to be the thrust of at least the first half of the rest of what I'm going to say here. And so when I say it's primitive, well, first of all, what's a basalt? Again, that's just to remind you why or we concentrate on the shergottites, which are the basalts, and why are they so important. And the first thing is that they're direct melts of the mantle. Now, something else may happen to them, and there's all kinds of things that can happen to them after they form in the mantle as direct melts. But in any case, these are, if we're going to find anything about the interior of a planet, it's going to be from these types of rocks that find their way all the way up to the surface, at least in a geochemical and mineralogical sense. And so they allow us to probe the compositions and other aspects of the source. And that's if we can determine the original composition. What's really nice about this guy is that we think it's primitive. And what does that mean? Now, a couple of words that have shades of meaning that get bandied about, and I'll use it probably in a sloppy manner, and excuse me for doing it. But there's the word primitive, there's the word primordial, and there's the word primary. And basically, we just mean these have come from they're very, very close to their original source. So the primitive material is a composition of the melt that was in equilibrium with. So they're going to be very geochemical here. So we talk about equilibrium chemistry. But this material was in equilibrium with the mantle source rock, and to understand how rocks form, of course, in the mantle. Just to go back a little bit, excuse me if I tell you more than you need to know, but or things that seem probably obvious. But I just want to make sure you all understand what I'm saying here. Or 30. So basically, rocks in the mantle form from a process known as partial melting. The whole area doesn't be a rather unusual circumstance if the whole rock source, mantle source, completely melted, because It's a mixture of minerals. Different minerals have different melting points, and in fact, any given mineral will melt over a range of temperatures because it's a complex compound, basically. So if we have primitive material and we look for ways to determine that that's what we really have, we can determine the mantle composition that the melt was in equilibrium with. And that's really a fantastic probe of the interior of Mars in this case. Now, just to remind you a little bit more Geology 101, there are processes that can affect magma composition after separating from the source rock. As the melt forms, it begins to migrate up through the crust, or what we really call the lithosphere, the solid, the rigid outer portion of the planet, and the crust, which is a distinctly different composition for the mantle. And as it migrates, it will settle into perhaps a magma chamber or a series of magma chambers on the way up. And of course, as it melts, it's going to cool off and start crystallizing things again. And so we can get crystal fractionation because things will float down to the or sink down to the bottom of the magma chamber, or just sink down the conduit as the magma is rising. And we can get assimilation of material from the surrounding crustal rocks, which perhaps have a lower melting point. They'll fall in. In fact, the magma will it gets up there by kind of forcing its way through cracks in the crust and making its own cracks, and stuff falls off into the magma chamber, so it gets assimilated. So there's lots of things that can happen, and so we end up with magmas that are the opposite of primitive. We say they're evolved. So those are interesting in their own rights because we can look at other processes, but what we're really interested here is a probe of the mantle is something where this hasn't happened on the way up. I'll come back to that and compare it to rocks where we think that that's happened, and again we'll learn some other things about it. Okay, here's our little guy here. Now there's a range of these olivine ferric. The reason they're called olivine ferric is just that they've got a lot of olivine. Olivine is the first mineral that will tend to crystallize out of what we call the primitive magma. It has a high melting point or a high crystallization temperature to it. In a lot of cases, so we get a lot of olivine in it. That's all that means when we say there's olivine ferric. Now, one way of getting a lot of olivines, we have to be very, very careful about this. One way of getting a lot of olivines in there is by this process, okay, of accumulation. So we've got to be very, very careful. And there are a number of these other olivine ferric sugatites, that just means Martian salt, that are definitely cumulates. And we have ways, which I'll get to here in a minute, of figuring out whether they're cumulates. And this little cute little diagram here, very, very cheap chemical, all it's showing is the composition, showing where we got magnesium, high magnesium at one end, and high in iron at another end. That's one of the hallmarks of something that's primitive. There's a lot of magnesium and iron in the mantles of terrestrial planets, and therefore in these mafic rocks. That's where the name came from. And the ones that, the more high temperature minerals, the ones that will crystallize out first or will melt last, are the more magnesium end members. And so having a lot of magnesium is, in this case, and that's what this is indicating, in the olivines indicates a fairly primitive composition as well. Yeah?
Mind if I ask, if it won't cause you to digress too much, what does mesostasis mean? I've seen it in papers and I never figured out.
The ground mass, just the stuff, everything else. So here we got some nice big olivines. We got some pyroxenes, which are also a magnesium and iron-rich mineral, and then the mesostasis is just everything else that's in between. And so those are the things that. And if you notice, actually, that actually speaks to how this rock formed. It was probably rising up pretty quickly to the crust, and before it started to before it erupted onto the surface as a surface lava flow, it began to crystallize out some of these. Now, in a lot of cases, as I showed in that previous slide, we'll get something sinking or floating ahead. But it looks like in this particular case, where we got lucky, and the whole thing erupted together as a whole. So these big, in other words, it was erupting so quickly that nothing had a chance to settle out. Okay. And then again, once the lava flow gets on the surface, then things can settle out there. And so it looks like we got a nice snapshot. Again, I'll come to how, just in a couple more slides, how we can tell. But we got a nice snapshot, basically, of the original composition. Okay, and so these big guys, they started to probably solidify on the way up, and the smaller ones a little bit later. Again, this thing must have been rising quickly. And then as it erupted onto the surface, it cools really quickly. And all this, there's the mesostasis, as you asked about. This is stuff that solidified post eruption. Some of these other larger crystals, say along the outsides, the rims of them may have also crystallized post eruption. Okay, another geochemical diagram, and probably this one's not too bad. This is what I was saying about the whole rock composition, and that's the first melts that the first thing that melts from the or the rocks that are again these rocks that are the source rocks down there are fairly high in magnesium, and so the primitive magma itself is going to be fairly high in magnesium. And this is Y98. This is just a list. This is a kind of a Caltech plot, which is basically something plotted against nothing on there. But do they have MIT plots like that? Yeah. Those are called the Caltech diagram. Something plotted against nothing. It's just the magnesium content, and then a whole bunch, then just a list of names there. And Y98, I'll call it Y98. It's the Yamato 9 zeros or whatever it was, for short. And it's fairly high. And we think the only ones that are higher are clearly ones that have accumulated more olivine in them. And so really this is about as high as one might expect the whole rock. So the whole rock is made out of the magma that formed down below and erupted onto the surface. So now I said something about the melts calculation. I'm not going to forget that. That's a big database. It's a big database where we take all this geochemical information, bulk compositions of basically experimental data, bulk compositions of starting materials, and then we see what things crystallize out and that sort of thing. And it's put together in just an enormous matrix, basically, an enormous matrix calculation. And you can plug in and do this online and plug in various parameters and say, well, I've got this whole rock composition. What would be my first, if that was a melt, what would be the first thing to crystallize out? Now, if that worked really well all the time, we wouldn't have to do any more experiments, obviously. But it puts us in the ballpark and say, well, are we in there? Now, the problem with this program is it blows up once you get outside of the really constrained parameters, because it's simply a best fit. As long as you're interpolating data, it's fine. If you're extrapolating data, that's a whole different story. But in any case, olivines are pretty well understood. Here's the chemical formula for the olivine up here. I'm sorry, I seem to have misplaced my remote control here. So I'm kind of doing double time here. Olivine just is, again, it's the most magnesium and iron-rich mineral, and again, first to crystallize out. And notice that, as an MgFe, is what we call a solid solution, so it can have variable amounts of magnesium iron in it, in ratio, atomic ratio to silicon knots. Okay, that's enough of that. Okay, now, so again, the first formed olivines, now this melt, and we're almost getting to the experimental stuff here. This melt is going to form, and then as it removes itself, this is more buoyant and rises up. As it removes itself from the source area, it's going to start to crystallize things. And so the first form olivines are going to be the highest in magnesium there. And as it proceeds, they'll grow, and the olivines become more iron rich. And typically what happens is there's not really enough time or space for the things to react, and that these things get rims with higher and higher iron contents, lower and lower. magnesiums. As I was trying to go and get it bigger. Okay. Now, if the crystals remain evenly suspended as the lava erupts, then the whole rock composition will reflect the original magma composition. If crystal settling occurs, then the upper, let's say this is a lava flow, flows out onto the surface, ignoring anything else that might have happened on the way up in the magma chamber or something. But if crystal settling occurs, then the upper portion of the flow will be more iron-rich because these crystals are more magnesium. And the cumulate, what we call the cumulate, that which accumulated, will be more magnesium-rich. Okay, so we did some experiments, and basically there were a few objectives to this. We took some. We wanted to first of all determine whether this meteorite, its composition, was a primary mantle mountain, and what map out what we call the PT trajectory. That is to say, the pressure temperature plot of its melting point, where melt last. Excuse me. Let's say as we cooled something down at any given pressure, what would be the temperature at which the first crystals form? And that would be called liquidus. And then characterize the mantle source. Okay, now I'm going to go through this really quick. We had methods that a lot of people think are okay. We put this in this little cappuccino machine here. It's called a piston cylinder that has a little furnace inside that you. Now this thing is about yay big. Has a little graphite furnace inside. You put your sample that's a synthetic mixture of the bulk composition of Y98. Needless to say, we don't use the Martian meteorite itself. It's moisture pressures for that. And this whole assembly is in there to be able to measure the temperature with a thermocouple. Put it in this machine and just basically subject it to a hydraulic press, just like a big jack, a hydraulic jack, and do some other things to keep things keep conditions constant, the oxidation state and such things, and then run this over a series of ranges of pressures and temperatures, and we get little things that come out like this, and for instance we get. Then what you do is you run it up, hold it at some pressure and temperature for some time, and then when we think, well, that's been long enough, we cut the temperature and cut the current and basically it quenches, and we get this little thing out, which is a glass, which is the quenched melt, and some crystals that have formed inside of our little capsule. Okay, and so it varies temperature. So we get olivine a lot of the time. And here's showing one with a mixture of olivine and the mineral pyroxene. Okay, so we put all this together. The first thing I want to point out, and I'll if you want me to, or I can just go back and remind you a little more Geology 101 about this. The cores of the olivines. Again, this is the so-called magnesium compass. This is a magnesium composition. Now it's plotted as the magnesium number, which is basically just the ratio of magnesium to magnesium plus iron, and it's atomic. Okay. Whatever. You just think of it as the concentration. Some relative units there. The dark. So this is the magnesium composition, obviously, of the first formed crystals. In this case, the blue symbols here are the olivines, and the triangles are pyroxenes, and then we have the glass composition as well. And also plotted on there, so for all the various experimental runs that we did, also plotted on there, this horizontal line is the composition for the actual rock. Okay, for the olivine cores, and if you recall, just go back real quick here. It's those cores, the first formed cores of the crystals will be the highest in magnesium. So this is these are what the very first ones are in equilibrium with that bulk melt, basically. Just a very tiny. So if we have just say 1% of olivine forms, we haven't really changed the composition here about too much, and that composition is going to be the first, and it will also be the highest magnesium content. Okay, so if we come back over here, that's what's plotted on here is this is the composition of the olivine cores. What's on, and so that's just a straight line. Now this is now the weight fraction of crystals. So we notice that in our run products, as we get to lower and lower weight fractions of crystals, that composition gets closer and closer to the olivine core composition. And what this is telling us, so we took the bulk rock composition. Now we had run some calculations that show that this may be the case, but we've shown this here now. We've with lower and lower melt fractions, that means we've got the crystals that are in equilibrium with the bulk rock. Okay, so this tells us that our experimental olivines, as well as our natural olivines, the very first formed ones were in equilibrium with the bulk composition of the melt. That tells us that we don't have a fractionated melt. Okay, at least not fractionated in terms of olivine and in terms of magnesium and iron composition. Okay, so that's a good thing. So that tells us that our whole rock is what was in equilibrium when the minerals when they first started to crystallize. And so here's this really complicated thing. It's actually pretty simple. This is what's called a phase diagram, and this is basically just showing the temperature and versus pressure conditions as to what phases, that is to say, melt, liquid, plus crystals that we're going to have at any particular temperature. This line here is the first formed crystals, the temperature of the first and which crystals have first formed here. And so as we took a pure melt, say, which we actually had a glass quenched melt, but as we lower the temperature at one particular pressure, this is the temperature that crystals will first start to form. And of course, as we get to higher pressures, this happens at higher and higher up. Now, interestingly enough, and this isn't unexpected as a petrologist, but might be from your perspective, that at lower pressures we'll have one type of, the first mineral coming out will be one type of mineral. In this case, it's olivine. And at higher pressures, it's pyroxene. And in between, we have pyroxene plus olivine, and there's only one point on this liquidus. And again, this is where the first formed crystals are. Only one point where we have two different minerals there, and that's what we call the multiple saturation point. Now, this is important for a couple of reasons. Now, we first showed that we've got a whole rock that is the whole rock is in equilibrium with the first crystallized minerals. Well, if our magma is pristine, that is, if it represents then what magma first formed, what melt first formed down below in the source region, the first minerals to crystallize out, the composition of that, and we go back, run that down, but we're going to go down to higher and higher pressure. Okay, that composition is going to be in equilibrium with these particular crystals. That same composition of crystals. Except for now, we're going back to down to the source rock, higher temperatures, and more importantly, higher pressures. Now, why do we look for this multiple saturation? We don't always find it. This rock first formed down, what's the multiple saturation point? What's the significance of that? When the magma first formed, it was in equilibrium, as I said earlier, with the minerals in the source. Okay? The minerals that were in that source is going to be a complex mineral assemblage. Okay? It's not just going to be olivine. There's the mantle of Mars, the mantle of any planet, is made out of more than just magnesium. It's made out of more than olivine. And so, in fact, it's got a slightly higher silica content. It's got calcium. It's got aluminum, various other. There's really the big eight: magnesium, iron, silicon, oxygen are the big ones, and calcium, aluminum, sodium, and potassium. And so we've got different mineral phases down there that have to be down there. So we would expect, so if we run down and find this multiple saturation point, we can find the mineral assemblage. It doesn't tell us what proportions, but this tells us which mineral assemblage that the melt was in equilibrium with, and it also tells us what their compositions are, because they're going to have a range of magnesium and iron contents. Okay, so in any case, that's why this multiple saturation point is really important. This must have been, now it's still going to be some kind of average, because the way that rocks form, the reason they melt in the first place is because they were high temperature and they came up and their melting point was lowered, and under decompression they decompress. So we get decompression melting occurring, and so they came from lower pressures, and they start to melt and partially melt, and then when there's enough melt there, these grain boundaries get interconnected enough that it will. Now, there's something else interesting about this. This is a very simple. This is still really simple. This diagram. I mean, I know it has a bunch of symbols all over it and lines drawn on it. It's really and probably about 3 too many arrows on there, but nonetheless, these are just showing us the phase balance. But basically, this is really simple. We've only got 2 mineral phases and the melt there. And we might expect the mantle of Mars down here to be have more minerals there. For instance, there's neither pyroxene or not this type of pyroxene. Pyroxene olivine will hold aluminum, and in fact, the type of pyroxenes that we found there, which are pigeonites, have a low calcium content. So those things had to go somewhere else, and there probably may have been a little extra iron and stuff in there. So basically, this is telling us something. And I'm getting ahead of my slide, so let me back up. Let me just say so far where we are, and then I'll continue saying what I started to say here. The magnesium content of those first formed experimental olivines are the same as the cores of the olivines found in Y98. That tells us that we've got at least an unfractionated magma or lava that hadn't fractionated at least after it erupted. We found a multiple saturation point. And quite often, if we don't have a primary magma, we're not going to find multiple saturation. This is giving us the conditions under which the range of temperatures and the range of pressures, which we can translate into a depth of formation, under which these things form, at least where they were when they were last in contact with the mantle source region. We conclude from these 2 things put together, there's admittedly a little bit of circularity to the argument, but the fact that one reinforces the other, we conclude that Y98, first of all, is at least is a primary melt and is not a cumulant rock, and we can tell from the depth of the equivalent depth of the multiple saturation point here, where it was in equilibrium with more than one type of mineral, that this was formed at a depth of approximately 100 kilometers depth inside of Mars. And these are really high melting temperatures, by the way. And so and there's a couple of other unusual things here about this, as I started to say. These are really high melting temperatures. Your typical terrestrial basalt will erupt at something like 1,200 degrees. Now, it formed also down fairly deep down in the Earth's mantle, although not quite that deep. And as it rose up, it cooled off. So it probably formed at somewhat higher temperatures. But this is actually somewhat higher than we'd expect. A typical, these will erupt though at about 1,200 degrees. So typical Hawaiian lava rock will erupt at something like 1,200 degrees Celsius. And their formation temperatures were a little bit higher than that, maybe 1,350, maybe as high as 1,400. But this is pretty hot, and that's not what we expected. And we calibrated and recalibrated our machine and reran lots of experiments over again and things like that. And we still come up with this result. And had another lab also ran these results. Okay, so let's come back to this fact: high temperature in only 2 phases at the point of multiple saturation. There's no, again, olivine pyroxene basically have magnesium, iron, silicon, and oxygen in them, maybe a little bit of calcium. But there should be a lot of aluminum down there. There's no aluminous phase and no high calcium phase in equilibrium with this magma. And this tells us that the combination of that and the high temperatures of their formation tells us that this represents a fairly sizable percentage melt. Now exactly what percentage depends on some assumptions, which I'll come to here in a minute. But we have a high degree of partial melting. Now what's typical on the Earth is somewhere between about 10 to 15%. And we look, in order to get all of our aluminum-bearing minerals gone, basically had to go into the melt. We've got to have, they will be the first melting point things, or one of the first minerals, but we have to have a high percentage so that they don't, so that doesn't, so there's nothing left in equilibrium with the liquid. So in other words, the upper mantles, at least to start with, ought to be a mixture of more than two minerals. And we don't see that in this particular case. We should have olivine and one or more pyroxenes and some calcium aluminum phase, such as feldspar. And then other minor minerals, phosphates and oxides. We don't see that. So with a high degree of partial melt of this aluminum-bearing phase, probably a feldspar is gone. Okay. Now, that conclusion alone, that's suggestive, but there's some other things, and I'm going to have to get a little more geochemical on you, even more so. There's other things. Now, there are other trace elements. Geochemists like to follow trace elements around. And we don't see, we can tell from isotope systematics, that is, we know that there's certain isotopes, say, of rubidium that will decay to isotopes of strontium. That those get fractionated because rubidium acts like potassium, strontium acts like calcium. That if we have liquid, we should have one mineral go, one isotope go into the melt, or one element go into the melt, and the other one stay in the mineral, and that will fractionate them from each other. And we don't see any of this, and this is based on completely different data set, but we don't see any fractionation of that rubidium from strontium. And so, and the point here, the presence of plagioclase, which is an important upper mantle aluminum, calcium and aluminum bearing feldspar phase, the rubidium would tend to go into the melt, and strontium would stay in the crystal phase. So since we didn't get fractionation of those things, we can assume that there was no feldspar around. Okay. All right. Well, the reason there was no feldspar is it all melted. It went into the. And we also have, all these things have a high magnesium and low silica content too. Well, all these olivine basaltic ferritides, that's what OPS stands for. So the greater the percentage of partial melting. Now remember, these were what we call ferromagnesian or mafic rocks. The mantle is even more mafic. And the first melt is going to actually, because the way elements partition, is going to have the biggest difference in composition between the melt and source region. But these are very, very high in magnesium, low in other things that are also high and low in we expect to be in the mantle. And so, and this is just a consequence of a greater percentage melt. That the greater the percentage of partial melting, the closer the melt composition is going to be to the source rock. And so just the fact that these are high in magnesium is suggestive, and the fact that we've shown that they're not cumulative. This particular one, some of them are cumulative, but this particular one is not.
Can I ask a completely naive question, or should
Sure.
I save it for later?
No, go ahead.
If the aluminum-bearing phase completely melted, why didn't it erupt too?
Oh no, there is in the ground mass there is an aluminum-bearing phase.
Oh, okay.
Because it's the lowest melting point, so it's also going to be the lowest crystallization temperature.
Okay.
So we have the big olivines and pyroxenes in the erupted lava, the rock that crystallized from the erupted lava. And in that ground mass that you asked about earlier, that contains an aluminum-bearing phase. In fact, that's feldspar, as well as more calcium-rich pyroxenes. Okay. So one thing about this, in order to get, again, I'll come to, and I'll probably go through it pretty quickly because I see in throwing in all my Geology 101 here, I've really been eating up a lot of time. But of course we did start late. But I'll kind of go through. I say there's a high percentage. How high depends on the assumptions we make. And one way to get really high percentage of melting is to do it over and over again. Okay, so we think that there's probably multiple episodes of melt production in producing these rocks, and this is going to have. So I want to go through this quickly, and I want you to just believe me that I did these calculations right. They're fairly simple calculations that we can do basically just based on how elements are going to partition between the source rock and the resulting melt, and we can look at the effects of different percentages of partial melt. And we'll just concentrate on these two elements here, magnesium and iron, and we can see what's going to happen to them. So we generally solve some, geochemists, we're more simple-minded with this. We just kind of think in fractions and stuff. So we just say, well, we've got this much stuff. If we can say, well, we have if a bulk composition. If we've got something of that's different from the bulk composition, we add some of this. We have to add X percentage of this to have the whole thing add up. Okay, it's called mass balance calculation. So this is just a mass balance calculation. Okay, and so what I've done here is simply look at what the magnesium content, and basically you can kind of think of this as atomic percent or atomic fraction of magnesium compared to iron in the melt. What had to be there? The first thing that we don't really know, we know the magnesium to iron content of the magma that erupted. There's a lot of discussion about what that should be down in the mantle of Mars. And some of that's based on sort of really big picture calculation, just the density of the mantle, and the mass distribution, the moment of inertia, basically of the mantle, what's distributed, how it's distributed down there, and how much magnesium and iron, because they have very different atomic weights. But there's lots of wiggle room in there, depending on a lot of other parameters. And that's part of what we're trying to get at here in doing this and working this into this other data. Okay, so basically what this says is the higher the fraction of melt is represented by Y98, then the lower the magnesium content was needed to produce that. Okay, again, so that as we get all the way down to somewhere around 0 fraction of melt, we're going to have something that had to have a very, very high magnesium content, and we'll get up to an enormous fraction of melt. We're going to get something that's very, very close to what the magnesium to iron ratio is in the melt. So the greater the degree of fractionation, the greater fraction of melt, the lower the magnesium content has to be in the mantle. Okay, but we think the magnesium content has to be fairly high down there. Somewhere actually a fairly middling number in here. And so you can see that if the number in the mantle is a fairly low number, and some people actually want to put it all the way down here at 75 atomic percent, or 70, then we have to have this enormous fraction of melt. Okay, nobody really thinks that at least in one stage that we're going to have this high of a magnesium content. I think I misspoke at the beginning there and said the opposite I wanted to say, but I hope okay, so these high fractions of melt, I mean really, even at these high temperatures, we're not expecting to have 70% melting, okay? That's really high. Again, on the Earth, we're 10 to 15% in the upper mantle. The only place where we might be getting up to around 50, 60% is on someplace weird like Io, which is being heated by the big moon of Jupiter that's being heated by tidal forces. intense tidal forces would really hitting the heck out of it. But from decompression melting, you and I can expect all at once that much. Okay, so the way to get that is that we probably had earlier episodes of melt. And so what's going to happen if we assume that the proven mantle, and like I said, there's a lot of people that really like this number of 75% for magnesium as in terms of magnesium, total magnesium iron atomic, and based on not geochemical but geophysical constraints. So how do we get a higher primitive mantle? And it would just take a higher, rather, source mantle down there. And so here, what we have here is what happens to the residual mantle as we take different amounts of melt out. And so, so if we had a previous event, this is an event before the melting event that generated our Y98 composition, our very primitive mantle melt there. What would this do to the residual mantle? So the higher and higher the fraction of melt. So again, the lowest fraction of melt here is going to actually not do much because you haven't really taken anything out. But if we start with, say, 75% magnesium to magnesium plus iron, that let's say something around a 40% melt would bring this up to, a little over 80% magnesium. All I'm trying to show you there, if you go back to this previous one, now if we start with an 80% magnesium in the mantle with our Y98 melting event, in order to get Y98, we'd have to have 40%. Well, that's still pretty high, but it's a lot lower than 70%. So I hopefully you can see where this is going. So if with more melt extraction, we drive the magnesium, previous melting extraction, we drive the magnesium content of the subsequent source further and further. The only problem with this is the mantle is less likely to melt third and fourth time because we keep removing this lowest melting fraction of it. So we've got to heat things up more now down below. So that's all this is. I'm just gonna leave it there because I have much time on this. Okay, so to continue on with this, these aren't the only experiments that have been done on analog Martian basalts to analog rocks to get at the conditions that are down below. I want to concentrate on some other things now besides just the melt compositions, but it is telling us that we've got to have a lot of melt. And that we've maybe had to melt a bunch of times. This is telling us that Mars is in fact really hot down below, which it's a small planet. One would expect a smaller planet to not be hot as a big planet like the Earth. Okay, so we have other data. Now most of our really good data is in the form of, I didn't go through the numbers, the tables are always bad things to put on the slide, but this is from the Gusev basalts, which one of the MER rovers, I forget whether it was Spirit or Opportunity, Spirit, I think. Okay, that's telling me to start moving faster. We started about quarter after, right? So
about 10 after.
10 after, okay, I'll move faster. Okay, so we do these same, we've got data from the MER rovers here, and we'll similar experiments to what I described for Y98 were done. And now we've got these at lower temperatures, but they're very different composition. And in fact, they were not as, if you see that they're multiply saturated in more, and we'll look at the very details there, but more minerals, and there's lots of reasons to think that they were probably somewhat lower percentage amount. But still at a fairly high temperature origin here. But the main thing is that they're at a very, very similar pressures to where this multiple saturation point. So very, very similar delta saturation. And so even though they're compositions, their locations, we wouldn't necessarily expect them to be the same temperature, but interestingly enough, very, very same pressure. We think what we're looking at here is the same depth to the lithosphere. But these results were really the first direct determinations of temperature and pressure conditions inside of Mars. And so we can take these and put them into geophysical models. And this was one of my collaborators, Walter Kiefer, developed a whole set of geophysical modeling and computer modeling based on a certain numbers of assumptions based on the distribution of heat-producing elements inside of the planet, the temperature that we'd find at the core mantle boundary, the depth to the lithosphere, and the temperature at the base of the lithosphere, and so now we've got these. We got these results from these and some later ones, which I guess I'm not going to be able to get to here, where we could input some more constraints that we hadn't had before. Now, this one I took from Kiefer 2003, the drawing, but actually these were later calculations that were. But so that the parameters that affect melt generation, this could tell us what we have to start with, basically, the temperature down deep in the mantle. So one of the things that's going to affect the melt generation here is actually where did the melt separate as the depth of the lithosphere. And then how much radioactivity, we kind of have an idea what a terrestrial planet is made out of. It's probably some kind of average meteorite. But how much of that is distributed between the crust and the mantle. And in terms of heat-producing elements, and what was the temperature at the base of the mantle. Okay, so we could now constrain that from these different melting experiments as 100 kilometers, and that assumption you just have to believe me. And the onset of melting requires very, very high temperatures down here at the base of the mantle. Obviously, as things rise, they cool off. So if they're going to end up at around 1500 degrees centigrade, they had to start out assuming that we had a rising plume of material coming up from the core mantle boundary, which is as good a place as any to think it might be coming from. We have to have a fairly high temperature, which is pretty hot. But and at first that might bother us, but so there's been some lower numbers, but not that much lower, from other geophysical models come out from there, and they weren't actually using this data. Okay, now the other thing, that's just to get a small amount of melt. If we're going to get partial melting, a large degree of partial melting, we have to have higher temperatures still. We have to start out at a higher temperature still. I mean, first, a greater percentage of partial melting requires higher and higher temperatures there. So we have to add about 5 degrees. So if we're talking very, very large percentage of melt, we have to have greater heating within the mantle, higher temperatures base. Now, there's from other lines of evidence, other things that people have suggested, that there may indeed be a concentration of heat-producing elements down here at the core at the lower mantle, at the core mantle boundary. One of the lines of evidence comes from the fact that it looks like and I took away the plots that were on here because I knew I wasn't going to have time to really talk about them in any hemisphere. But these heat-producing elements like uranium and thorium, there seems to be some missing in the rocks that we're finding at the surface, and that tells us there must be maybe a reservoir of them hidden down there that we haven't sampled. If that makes sense. If it's missing, it must be there. But anyway, and Mars, just from a comparative planetological point of view, Mars, we know that the moon had a magma ocean. We surmise from that the Earth did too early on, and through some other things which maybe chemically oriented, but we know that we have reasons to believe that Mars may have. And people just taking what we think is a good Mars composition and condensing out dense phases, such as garnet, or even better, a mineral called perovskite. That these are very, very heavy, and these like to take up things like uranium and thorium, and these may have concentrated down at the mantle. So even though Mars is small and should actually lose heat, and in fact, its upper upper part of the mantle probably is considerably cooler. At least its lithosphere is. It's got a thicker lithosphere than the Earth does. But may have concentrated heat-producing elements way down into its interior, so that although we're not producing widespread mantle convection everywhere like we are inside of the Earth, that deep-seated mantle plumes can actually start out very hot, even though it's a smaller planet. It should, all things being equal, cool off faster. And so overall, it may be cooler, but down around the core, that we should have a concentration of heat-producing elements. On that note, okay, so I'm going to skip a lot of what else I was going to say and just leave these as for the sort of the first conclusions I want to make. There's been some other work on this, so I did put it on the slide, but from completely different lines of evidence. It's thought that the core inside of Mars must be fairly hot, and that's simply because now Mars doesn't have a significant magnetic field, and now the Earth does, and that's not just because it has a molten core, but because it also has a solid inner core, and it's the crystallization of the inner core that drives core convection to generate the Earth's magnetic field. So if you have if you don't have a magnetic field, that means the core has to either be completely solid or completely molten. And since there's certain things, just saying what we think Mars's mantle or core should be made out of, it seems unlikely that it's actually completely solid, and that's a surprising result. Again, it's from different lines of evidence that are on here, but different considerations. But if we combine this from all that we've learned from melting these olivine fluoride sugartites that had to have formed at higher temperatures, had to form higher percentage of melts, had to melt over and over again, and must have and the implications of concentrating heat-producing elements all the way down at the very base of the mantle, which would keep the core nice and toasty down here, so it could also stay molten. Now, it would also have a higher sulfur content than the Earth's core did, so it would have a lower melting point. So that's also makes it. Okay, so I'm going to skip all the way through all this stuff and just go to the conclusions. I wanted to talk about different mantle reservoirs, but we'll just leave all that and just continue. All I was going to say is we have different rocks that really very different geochemical makeup than the ones that are described here at the very beginning, indicating that we have probably different sources inside of Mars, and they may either be different mantle sources or they may be the crust in the mantle. But I don't have time to do it justice to get into the ins and outs of that, so we'll just summarize here. So we've demonstrated that this meteorite itself is a bulk composition, represents its parent melt, that it, we think, logically is a primary melt of the Martian mantle, represented multiple episodes of fairly high degrees of partial melting, cumulative high degrees of partial melting, and implying high temperatures at the core mantle boundary of Mars, and this has these high temperatures have required a revision of our views of the Martian interior, but they do go hand in hand with some other lines of evidence that are suggestive of higher temperatures deep down. And I didn't get the rest of those conclusions, so I'll stop there. Thank you. Oh, that was okay. So there you go. Any questions? Yeah.
Where do you get the 100 kilometers from? So is that assuming that things happen on Mars the same as on Earth?
Okay, it comes from knowing the gravitational field of Mars, assuming a crustal thickness of about 50 to 60 kilometers, and that the rest has to be mantle composition. That 50 kilometers comes from taking an assumed bulk composition of Mars and removing X amount of basically basaltic crust, and saying how thick, how thick that would have to be. So that's another mass balance calculation. And then, and so you've got 50 kilometers of basalt density, and then you've got X kilometers of what would be mantle density, and compare that, and given the gravity of Mars, I guess it's 100 kilometers. Yeah.
I understand that iron sulfide, that Mars would help you lower the core melting temperature and therefore help you keep it liquid. I've heard from various sources that some people think that for other reasons that iron sulfide is higher in percentage in the Mars core than in Earth's core. What are some of those other lines of reason?
Well, Mars is definitely higher in volatile substances. Although, in terms of the amount of atmosphere, it's probably lost stuff that a lot of things that it outgassed. And it may have outgassed less than the Earth did, and whatever it outgassed it lost. And so but just given the fact that it's further out in the solar system, it should have a higher percentage of volatiles.
What was out, nebula that far out would have more volatile materials.
Yeah, and we also see it at the surface. I mean, Mars is, it's the red planet, but it's really an yellow-orange planet. And the red is, of course, rust, is iron oxide. But the yellow and orange really is a lot of sulfur. So the rocks that are at the surface and the Martian dust and sands blowing around the surface actually contain quite a bit of sulfur, much more so than the Earth. In fact, if we look at a lot of the data from the rover missions, and I'm losing my voice here, the rover missions, where we found what appeared to be water-formed evaporite minerals. These were very highly acidic, basically, essentially a concentrated sulfuric acid waters. So no doubt there's a lot of sulfur, basically, in Mars. And if you think about how it partitioned between metal and silicate, for instance, or iron sulfide, we should get a pretty high core composition. Yeah.
Can I ask a very naive question from a non-geologist here? Did I understand you correctly in saying that when you get a magnetic field from a planet, it implies that the core is partially liquid and partially solid? It's something to do with the interface between the liquid and solid. Right.
It's basically the heat of fusion of liquid going to solid. Because a metal core, and this is just what my geophysicist friends tell me, because I'm just a geochemist, but the metallic core should conduct heat very readily. Okay, you would not expect the type of temperature gradient inside the core as you would inside the mantle. As you know, we go down just in a deep mine. You don't have to go very far down into the earth, where it gets pretty hot, and not even down to magmatic temperatures. Okay, and so that's because there's a fairly shallow, steep, depending on how you look at it, geothermal gradient, temperature gradient, as you go with depth, and that's simply because of the way rocks conduct heat and convect heat. But as you get down into the core, where it's metal, conduction of heat is much more efficient. And so you're not expecting this type of gradient. And so to set up convection inside of the core, you need a heat source. And that heat source in the Earth, to really drive convection and therefore drive the magnetic field, has to be the heat of fusion of the metal.
So did you say that Mars did not have any magnetic field now?
It's got a low magnetic field. It's got magnetic rocks that appear to be older. This is just from orbital data that we can find localized magnetic. Of course, you would expect magnetic minerals to form, and they're going to get. But it looks like these are fairly old, and perhaps Mars may have had some sort of magnetic field.
Yes, but this is one I'd heard, that it may have had a larger magnetic field in the past. Yeah. So what it means then is that it's it is more of the core is now solidified, so it's gradually solidifying.
That's
Yes.
one
Yes. So it's,
that's one possibility.
but it can't be totally solidified, because as you say, there must be, to have a magnetic field at all, and because of the temperature down there,
Right.
there must be some heat.
Right.
So in
But-
other words,
but-
it's,
But let me just back up. The
Yeah.
magnetic field that's there is a remnant magnetic field. And we
Yes.
don't know what generated it. It may have nothing to do with the core at all.
okay.
I mean, it could have, you can get saline, solutions, high salt solutions, which could generate electric currents as well, right? Just electrochemical electrochemical processes that might generate that. But I mean, it does seem puzzling that, well, if it had a magnetic field in it, and that was in the rocks, and now it doesn't have one, it seems like that should mean that the core may have solidified.
This is what
Right.
one is normally
But
told,
but
isn't it?
but that presupposes actually two things. One is that the magnetic field was originally from the core, and actually it had to have been fairly weak. And number two, that all things have to cool off. If we've got these heat producing this blanket of material, it's possible we may have been heating up the core, which is weird. It's counter.
mean like
It's counter to the
reheating
usual
again?
logic. Actually, it's counter to the usual logic. There's no doubt about that. But then, in fact, maybe the core is heated up, or its melting point has gone down, which is another way of looking at it. Its melting point for some reason has gone down by, say, injection of more sulfur.
Basic geophysics is, you need to get a planetary magnetic field, you need a core that's made out of something that's conductive, okay? And the easiest way to do it is metal. And it has to have something that drives convection in that core. And that usually involves a temperature gradient.
Yeah. In Jupiter, it's metallic hydrogen.
Yeah.
But you can get weak magnetic fields from solutions, electrochemical solutions too. So that aspect's actually still is really quite mysterious.
And still in much dispute.
Yeah, absolutely. Oh, no doubt about it. Yeah. So I was kind of weighting this on the. I think the core is a null side. That's better with. What else?
Okay.
That's it.
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 Okay.
That's it.